Hey guys, welcome to Population Ecology.
With your teachers, Miss Pranky and
Mr. Harmson. Dun, dun.
So today we're talking about how to describe populations. In order to do that, we need to actually identify what a population is. So a population is going to be a group of organisms of the same species that interbreed and live in the same area. In order to identify a population, you need three things. You need to identify the type of individual, the location, and the time. So for example, I could talk about the population of pigeons in the loop in 2018. Something to note here is you just want to be very specific so people know what population you're talking about at what time.
All right, so let's talk about population density and population distribution. Those are two very different ideas, and the population density has to do with the number of individuals per unit area. And population distribution has three big ideas, and that is random, uniform, and clumped. At the very top, you see this beautiful field of flowers. And generally, you're going to see vegetation in a random distribution. Below that, you see these awesome emperor penguins, and they are almost all equidistant, and they're really uniformed in their distribution. So obviously uniform is a great word for them. And then you have clumped, and that's a big ball of fish in which there's no really way to discern how they're distributed other than just kind of in a big group.
Yep. Now we want to talk about factors that are going to affect our population growth. So when we study populations, there are two things that we want to look at. We want to look at the rate at which the population is growing, and then how many individuals are in that population. So in order to figure out growth rate, all you have to do is you have to take the number of births at a given time and then subtract the number of deaths, and that's going to tell you how quickly that population is growing. Then in order to figure out the size of the population, you need to look at four things. If you are looking at births and immigration, that means that your population is going to be increasing. If you are looking at deaths and emigration, which is moving out, then your population is going to be decreasing.
So the big takeaway here is there's two ways in which populations go down, and there's two ways that populations actually go up. So that always strikes this great balance in populations.
Yes.
All right, limits to population growth. We're going to talk about carrying capacity and limiting resources. So a carrying capacity is the largest population that a given environment can support indefinitely. So what does that mean? It's a maximum number of organisms that an environment can support, right? The tundra can only support so many caribou before they braze it and die.
And there's nothing left for them.
Right. Limiting resources, it's a particular natural resource that when limited, determines the carrying capacity of an ecosystem for a particular species. And we kind of just talked about that in our little caribou tundra example.
Yes. So the big thing to know here, you guys, is that limiting resources, which is going to be the resources that you use to survive, like your food, your water, your shelter, are going to determine the carrying capacity of an environment. Here we're going to look at two things that are limiting resources. So we have density dependent factors and density independent factors. When we talk about density dependent factors, that means that these things depend on the density of a population. So the more densely populated it is, the more competition that there's going to be, the more likelihood of parasitism happening, the easier it's going to be for disease to spread, and the easier it's going to be for predators to hunt their prey.
So when you have a nice distribution of the competition, parasitism, disease, and predation, it strikes a great balance in that ecosystem. Yeah. So that's a healthy ecosystem.
Yes.
When you look at density-independent factors, those are all things that consider weather, yes. Right? So it doesn't matter how dense a population is. If a forest fire ravages the San Fernando Valley, it is going to take everything out, the trees and generally the animals included. A hurricane comes through, it's going to bring high winds and break trees and scatter populations of animals. Some might not make it. It's going to happen regardless. Same with weather in terms of precipitation and temperature from hot to cold.
So here we're looking at exponential growth, which is going to be a J-shaped curve on the graph. For exponential growth, this is how populations are going to grow under ideal conditions with unlimited resources. So the larger the population gets, the faster that it's going to grow.
So logistical growth. Now we're looking at an S-shaped curve, and they call it an S-shaped curve because it obviously is shaped like an S. What you're going to see here is populations grow pretty quickly, and then they're going to plateau where you see that perforated line that's called the carrying capacity. And you're generally going to see those populations level out because the resources that are available to them are going to be somewhat limited because of the population growing so fast.
Yes. So something I want to point out on this graph, what you see with logistic growth is it's still going to have a point of exponential growth. But like Mr. Harmson said, it's still going to hit that carrying capacity and level off at some point.
All right, survivorship curves. The first one we're going to look at is most individuals live to adulthood and then die. So at the very top, you're going to see a really high birth rate, and then survivorship continues to stay pretty strong until they get to around the middle of that curve, and then they start to decrease because populations die.
Yes.
And it's the opposite on type 2, which is equal chance of death at any time. So what you're going to see is a lower rate of survival. At type 3, you see a nice little J curve that indicates that the survivalhood of juveniles is pretty low. However, as you get down the curve, once you get past that juvenile stage of their life, the likelihood of you surviving to later life goes up.
Yes. So he actually meant type 3 there, not type 2. That's
Sorry.
okay. For type 2, this is going to be an equal chance of death at any time. So there's no higher likelihood of organisms dying early in life or later in life. Got to erase my stars.
So survivorship patterns. We have two different types of strategies here. We have R-selected strategies and K-selected strategies. So what do you think is going to happen here? We have this awesome clownfish that's guarding its nest, right? So if you're an R-selected strategist, you are an organism that gives a high volume of offspring.
Yes.
But you don't put a lot of time or energy in raising those offspring. So a fish is a great example of laying thousands of eggs, and they're generally left on their own to figure out how to operate in the environment.
In hopes that at least some percentage of that offspring will survive. Not all of them, but some of them will. These organisms are also going to have shorter lifespans, and they're just going to have a higher infant mortality because they are laying like thousands and thousands of eggs, hoping that some of them make it.
And if you're a K-selected strategist, now generally these are going to be mammals because they don't give birth at a high rate. They give birth to fewer offspring. However, they spend a lot of time raising their offspring. And if you're spending a lot of time raising your offspring, you're expending a lot of energy in that process by teaching them, by feeding them, nurturing them. So the two differences are drastic, and one's neither right or wrong. It's just how they've adapted in their environment.
Right. So for K-selected strategists, their strategy is if I invest a lot of energy in my one or two offspring, the likelihood of them surviving is very high. And then if you're an R-selected strategist, you have lots and lots of offspring, but I'm not going to invest any energy, and the odds of some of them making it are high. Not all of them, but some of them. So looking at that, we just want to point out that this is a spectrum for these strategists. So not every organism is going to fit perfectly in one or the other. For example, if you have a rabbit, they may have 12 offspring a year, and they may invest a medium amount of time, and then maybe like 6 months, but then after that, they're on their own. Versus an oyster who's going to lay over 500 million. Do they have eggs? I said lay. Do they really?
Yeah.
I don't know that. They lay over 500 million eggs a year, but they invest very little time in them.
And then if you look at a chimpanzee, they're only having one every 5 years. And they're expending a ton of energy and time in raising that offspring.
Yes. So the main point of this is just to understand the two different strategies and that these are adaptations that different populations and organisms have in order to increase the chances of survival. So if you guys have any questions, please reach out to myself and Mr. Harmson. Please make sure that you fill out this note sheet and submit it on Schoology for us.
And that is your wrap up on population ecology.
Whoop, whoop.